I am Guray Yildirim from Istanbul, Turkey, and today I will talk about improving developer experience in Kubernetes and container world. So the title is Development in Kubernetes, Containerizing with GEPP, and Developing with Telepresence, Scaffold, Tilt, Okteto, and some other tools. Here are my contact information. Feel free to contact me in any case. So, let's start with talking about myself. I have been working as a self-employed SRE and DevOps consultant, and I have more than 5 years of experience in container world, specifically with Docker and Kubernetes. And prior to my current experience, I have worked as a GNU Linux system admin, as well as embedded system developer. So I have been writing some codes in Python for more than 10 years, as well as C and C++ in some cases, especially in embedded systems. I am the author of 3 books, and the last one is about containers and Docker, and the other 2 ones are about IoT, Raspberry Pi, and Python. So I combined these things together, these 3 things together, and produced some projects in that books. And finally, I am a HashiCorp ambassador as well as the leader of Docker Istanbul community and Hack Istanbul organized. So what's the plan for today? Today I will talk about the problem definition because we should talk about some developer experience improvements by defining the problem and questioning why it's a problem. And afterwards, we will talk about possible solutions. I gave some names in a couple of seconds before. And maybe when we should choose or when we can choose what solution. And I will try to show some demos as well as finally I will talk about GEPP, which is an open source project started by me and helps people to containerize their application as well as deploy them to a Kubernetes cluster. So I will talk about a couple of disclaimers. First of all, there are a lot of tools other than the tools I will cover today. So I am not covering all of the available tools here, and I will only talk about the open source one or open source components of them because some of them are also have some commercial offerings or paid offerings. So I am focusing on the open source parts of that projects. And there are a lot of cases. I know there are a lot of different companies, a lot of different people working with different programming languages, different frameworks, and different environments. I cannot cover all the cases here, so we will stick with some scenarios, but I will try to give as much as info possible to get started by yourself. And there is no specific order because I selected the order based on my experience. So the first tool I will show you is the tool that I have more experience than others. So no special meaning for that part. By the time you are watching this video, I will reading your comments. So I am wondering about how many of us are working as a developer or how many of us have worked as a developer before. So by the time you are writing your comments, I am continuing. How the software delivery is started. Actually, we all know that, but it's required to get some context in our topic. So we started by deploying our codes physically. What I mean by saying physically is we build our code, we copy it in a portable media, and afterwards we get closer to physical server, mounted, attached the media, and copied that file, run, and we actually iterated through that loop again and again. Afterwards, networks are evolved. We had access, we had chance to upload our projects directly to the servers, and this caused us to uh, gain some advantages physically. So we were just able to upload our code or upload our compiled binary to the server and run it remotely. And after virtual machines come to our life, actually it gets more easier because spinning up a new virtual machine and deploying some things uh, are now possible. And after trying something or after some breaking change, we can just remove the old server, or if an error occurs, we can just remove the new server without accessing physically to any server. And afterwards, finally, containers come to our life. We can spin up a new container in a couple of seconds, if not less than a second, of course. And we run our application in that container. We can try things, we can break the container, break the things in that container. And after our job is ended with that container, we can just remove it in a couple of seconds. So it speeded up our development environments or our deployments. So these things help both developers and sysadmins as well as DevOps and other IT fields. But in the same time, in the CI/CD world, there are a lot of different tools exist, like Jenkins, Google Cloud Build, GitLab CI, GitHub Actions, Azure DevOps Pipelines, Drone CI, and a lot of different tools or products are available in that market as well. And we have started to make immutable builds, which will not be affected from previous builds. So with containers, actually, this become much easier than before because we spin up a container, build our code in that container, and afterwards remove that container completely. So no side effect, no forgotten artifacts, no other effects as well. So it's a clear solution. We are running unit tests, integration tests, functional tests, smoke tests, and other tests in containers when possible. And it will also help us to isolate builds from each other and testing more properly. But in this equation, there is some gaps that developers need, because developers benefits from these tools after they run or they try code in their computers. What we are trying to get is running the code directly in our computers. And if the code is running properly in our computer, we want to make sure about it will behave exactly the same way in dev, stage, prod, and all of the other environments. So the question is, how long does it take to go into production when you push a change to your repository? The requirement is developing in real environments. By saying real, I mean that the environment should be close to the real dev stage or prod environments. So we are talking about setting up a development environment which should be same or as close as possible to production environment. And what we need is short time intervals when we change a line. For example, when I change a number in a line, or when I change a variable name, or calling a method, uh, I I should just I should just press run or debug button, and I should see the effect instantly. I don't want to wait for CI/CD pipelines to be completed to see how my code behaves on a real cluster. So I want to get feedbacks instantly as fast as possible. I want to test my code in production production-like environment, and of course reducing the development and production quality. So what's the problem? An example workflow when we are training our code in a real cluster consists of these steps. We are committing our code after we change something. We are pushing our code. It triggers CI/CD engine we are using. Maybe the CI/CD engine is looking for a suitable agent or dynamically provision an agent to run our build, and afterwards it builds our code or it runs the tests. It will create a container image and it will push the image to a container registry, and the servers that will run our code will pull the image from that container registry and update the deployment. So it's an example workflow, an example pipeline when we are trying to see our change in a real cluster. But development frequently requires trial and error steps. So we are updating one line, maybe one character at a time. And we want to see its effect, how it behaves. And if we can see the same procedure, the same effect in a real cluster, it will help us to develop applications that will behave the exact way in their production and stage environments as well as our computers. And the pipelines consumes a lot of time, actually, especially if you have a lot of different steps and checks or tests. And this causes negative developer experience, of course, and reduces developer performance. So what's the possible solution? One possible solution is running a local cluster in your computer. We will go on that solution, but not every time this solution works because many stacks include a lot of different parts. For example, there may be hundreds or thousands of different microservices that have written by you and your coworkers, different teams, maybe different companies, and you should work with many of them to test your application properly. Mocking them will not help you or may not help you in all cases, so we should deploy them in our computer. As you guess, our CPU, RAM, and disks may not be sufficient for deploying all these microservices. And also there are some databases, there are monitoring systems, agents, there are service meshes, and a lot of other stuff as well. So our laptops gain some temperature, and we may still not be able to run all the stack together properly. Also, when the other people updates their code, we should track them and update the code, their code working on our laptops as well. So it requires some tracking mechanism, but even if we solve it in an automated manner, still it's really it may be not feasible to run all the services in our computer. So before going to the solutions, I will go on an example code that we will try to develop or make changes on a real cluster to show how we can benefit from the tools that will solve that problem. So it's a Python code. It's a basic Python code written in Falcon framework and Python programming language. The code is, as I said, using Falcon framework, and it's getting an environment variable named waitTime and default values. Two means that when you send a request to that API, it will sleep 2 seconds. It will not give you a response in 2 seconds. And after 2 seconds, it will return you a random number between 0 and 100. So this is the result format. The lower limit, higher limit, and the number will be returned to us. We will show the returned value again and again. And the number is selected using random.randint, which is a pseudo-random generated by Python. So we are sleeping 2 seconds by default, but if we define a wait time environment variable, we can overwrite this value, and we can, for example, if you want to respond instantly, we can just set wait time environment variable to 0, and it will just produce the random number and returns it. And also, the endpoint we should connect is /number. So we will make requests to /number, and it will give us the random number after 2 seconds. And here is the Docker file. It's a basic Python Docker file using Alpine Linux image and Python 3.8 version. Unicorn is used as an application server, and here is the reload parameter. If our programming language and tools are supporting hot reloading, it is very useful to put it here, because when we change our code, it will automatically watch in container the change, and without restarting or recreating the container, it will automatically reload our application, and we can just reload our web page or resend our request, and the new code will respond us properly, or how it behaves depending. And afterwards, just requirements file like POM.xml or CSProc files, and the other Python files, as well as source directory, is copied into the image. So the requirements are Falcon and Unicorn. Falcon is the framework we are using in Python to develop simple APIs, and Unicorn is our application server. And in order to deploy that, we will use two commands in Kubernetes to create a deployment and create a node port service object. So let's start with creating the deployment. So kubectl create deployment is my command, and to be in sync with the slides, let's take a look. It's called random API, and the image is the demo 1.0. Let's check. Yes. So afterwards, I will expose that deployment as a node port object. kubectl expose deployment random API, and type is node port. I will also provide the port to 80. Let's check. Yes. So kubectl get services will give me the node port we are currently using. So let's connect one of the nodes from CURL using CURL. Here is the IP address, here is the port, and I will add /number at the end and press enter. Okay, let's check how it's going there. kubectl get pods. Okay, I have just forget a pod here. Let's delete that one and wait for its deletion, and afterwards I will send the request again. Okay, let's try again. It's waiting 2 seconds, and it's returning the random number to us after 2 seconds. And we can actually measure it by using time command, and it will last, actually it lasts 2 seconds approximately. So we deployed our application. Now we are coming to possible solutions. The first one will be the telepresence, but before that, there are two main approaches that I will cover today. One of them is running the code in the cluster and attaching the running code by streaming its logs, forwarding its ports, and updating our code in a live manner. When I change something, it should be synchronized to the cluster and rerun our application. And the other approach is running the code in my computer, and all the requests coming to the cluster should be proxied to my computer, and all the requests I send should be proxied to the cluster. So there should be a two-way proxy in the cluster that will help me to run the application in my computer, develop my application in my computer, but also allow me to access all the Kubernetes resources from my computer, just like I am in the cluster. We will talk about that. What we are trying to do is bypassing CI/CD pipelines. After we prepared our code, we will create a commit object and push it, and afterwards CI/CD will still run. But before that, we are trying to speed up our application development processes in our computers. And we want to see logs from a real cluster instead of our computer's local dev environment. So think it like you are in a pod in your dev cluster with your computer and writing code. It's what we are trying to achieve by using these tools. And we want to connect real database, real other services, and real different environments, monitoring tools, agents, etc. So the solutions I will talk about is listed here, and let's talk about the first one, which is Telepresence. Telepresence allows you to run application directly in your computer without installing anything, and it doesn't require any configuration files. Just running Telepresence, maybe with a couple of parameters, but not much of them, should be enough to run Telepresence and benefit from its features. So it will allow you to access mounts, secrets, config maps, environment variables directly in your computer. You will run your application just like you are in the cluster, but you can use your own tools, your own commands, your own ID, debuggers, and all of the stuff you have in your computer. You can also connect services that you defined in Kubernetes directly from your computer. And Telepresence doesn't require a container registry to push your images. It will swap a pod in your deployment with a proxy. So any request come to that proxy will be forwarded to your computer. Any request you make a Kubernetes service will be proxied from that pod to the real cluster. So it's the way that Telepresence provide us these features. And we can run a container in our computer instead of tools, command line interfaces, IDs, etc. We can just run a Docker container, and the container running on our own computer will pretend like it's in the cluster physically. So let's talk these features in a demo. In order to get started with Telepresence, we will just write this command, which is telepresence expose 88. It will help us to achieve many of these features that we have talked so far, which is now I should be able to access a lot of different mechanisms in cluster. For example, I should write kubectl get services. Let's check them. As we see, Telepresence provided us a different shell. Now the shell is running in my computer, but I can access everything in that cluster. For example, I can just CURL to random API here and /number endpoint. And after 2 seconds, this response is come directly from the cluster passing through the Telepresence proxy that deployed in that cluster. In order to see that proxy, kubectl get pods will be enough to understand what's going on that cluster. So our requests are proxied through that proxy pod. So I can directly connect a service running on Kubernetes from my computer. And the second example, I will just close that and I will rerun the telepresence command with swap deployment option. The swap deployment option swaps the pods of random API deployment in that cluster, and any request coming to random API will come to the Telepresence pod, or I can run the random API code in my computer and the random API can connect to any resource in that cluster. It also can directly access any services, any mounts, secrets, config maps, and other stuff that are residing on Kubernetes. Let's get a list of services, and actually let's try to get environment variables. Here are the environment variables that Kubernetes defined for our pod. I can access the environment variables as well from my own computer, just like in the cluster. And here are traffic port, TCP address. Let's try to send a request to here, and this response has come from the cluster and traffic pod directly to my computer. So I can access everything, almost everything from my computer. And after this example, I will clean up that and I will create a different secret, a different object, kubectl create secret, and its type is generic and its name is important because we will use it in a minute, and it is from literal token equals my secret, so it is our key value pair. So I created, okay, I have already created that one, and we have Kubernetes deployment YAML file in that case. I will just deploy that, apply. It will override the random API object. So I have updated random API, but that time I included the secret as a volume and mount path is /secret. So now I will rerun the telepresence with swap deployment option, and I will just swap random API deployment pods with telepresence proxy, and now I should be able to access the same secret from my computer as well. Let's try. It's a telepresence root. Let's see. Telepresence root gives us an address, a path, that we can reach every volume or config or secret in Kubernetes. So here we can just access the secret path, and here is our token. Let's see the token value. Here is my secret. And if we want to see all mounts that available, telepresence mounts will give us a list like service account and secret. So of course we can use service account here as well. If you want to run Docker containers, here is that command. Random API will be switched by a Docker run command, and the container will run in our computer. But just like we just seen, it will behave like it's running on the real cluster. So the second tool is Scaffold. Scaffold is an open source project from Google, It is requiring a YAML file named scaffold.yaml. It will watch the changes in your current directory, preferably the repository, and when you make a change, it will rebuild a Docker or container image, push that image to a registry, and update the deployment on the cluster, and cluster will pull that image and run your new code. So, what Scaffold can do? Scaffold can build the image from on your computer, but sometimes we don't have enough internet connection bandwidth to upload images frequently, or maybe computing power. In that case, it can build the image locally as well as remotely on cluster, or it can use Google Cloud Build to build the image when we change our code as well. Its ideal workflow is git clone and scaffold run will deploy our applications in a real cluster. So it is intended to be a CI/CD tool as well without any additional effort, and it also supports remote debugging. It also has Cloud Code extension for Visual Studio Code and IntelliJ. And Scaffold Init will be the first command I will talk about. It will discover your repository and generate a scaffold.yaml file for you. Scaffold Dev will start a development environment that will continuously create a new image, push them to the cluster and update the deployment, or syncing your files without recreating or rebuilding a Docker image or container image every time. And Scaffold Run, as we talked before, is running it as a CI/CD tool. So let's start with Scaffolds Demo. I will close Telepresence, and Scaffold Init will scan our repo, and it asked me to choose a Docker file. I chose it. It prepared a Docker file, Scaffold YAML file, and if I press yes in that case, it will save that file to scaffold.yaml. So here is the image. It will build and push, and afterwards it will deploy this deployment YAML file instead of us. So when I run scaffold dev, it will build the image. It is pushing the image, and it will deploy the YAML to the cluster, and it will start to stream its logs to us. Yes, here are the logs are coming. I am closing it and just continuing with leave synchronize. If you want to synchronize our code with the cluster without rebuilding image on code changes, just writing the sync part in artifacts and which files to be synced will be enough. Let's talk about demo resources, scaffold YAML.1. I will copy that file. Let's see what's inside. Sorry, it should be 2. Yes, it's the same as here, and when I run scaffold dev in that case, it will automatically start synchronizing my code without rebuilding image every time. So if I will change something in my code in another terminal, it will automatically synchronize. And the other tool we will talk about is Tilt. Tilt has a great web UI. It has a config named tilt file, but it doesn't require restarting tilt itself to recognize the updates in tilt file. Tilt file is written in Starlag. It's a Python dialect. So if you are familiar with Python, it's really like a Python code. So it's working like recognizing local changes, pushing them, deploying the image to the cluster, or it also supports synchronizing files instead of building images every time. Synchronize is called live update in that case, and we can see everything in its UI. So it's an example tilt file we will see now. The first command I will write is tilt up. It will run its UI, and what I should do is just make a port forwarding. Let's copy that port here. Okay, then let's connect to its port to see what it provides to us. And here is the interface of tilt, and here I will close it, but I shouldn't, I don't have to close that pane as well. And let's continue with its features, and I will deploy a tilt file, a non-empty tilt file as well. So here is an example. I am allowing default context. It's a safety mechanism to actually help people not mistakenly deploy their codes to production environment. Here is the YAML files that tilt will deploy to cluster. It will deploy an image using that context, and we are just forwarding a port to our local computer from that Kubernetes resource. And if we want to sync live, Docker build, we can add live update part to Docker build, syncing the current directory to /app, and if requirements.txt is changed, it should run pip install.rrequirements.txt again to install new dependencies. So the rest are the same. Let's just copy the tilt file here and run tilt up again. And afterwards, okay, no need to refresh, but I refreshed. Now it started streaming logs. It also supports a lot of different microservices at the same time. We can just select the relevant service here and see its logs, its build logs, its events, and a lot of different details in that screen as well. So it helps us to actually deploy or manage our application or see our application state in a great web UI, as well as providing synchronizing or continuous development changes in one product. There are a lot of different features as well in every tool that I showed here. And the other one is Okteto. It automatically generates its YAML file like Scaffold. It can be use any image as a dev image. It will run that image in the cluster. It will forward ports from your computer to the cluster, or it will forward a port that the container in the cluster listens to your computer as well. So two-way port forwarding is possible, and it's synchronizing your files in your computer to the cluster using Syncting, which is a great project also. And the Squash is actually enabling debugging by attaching running programs in Kubernetes. And there is also draft I want to talk about. It is archived in GitHub, so I am passing it. So the last one I will talk about is GEPP. What we require to getting started, almost all of these projects, is a Docker file, a Kubernetes deployment, Kubernetes YAML files, preferably if you are running locally, a multi-node cluster, and ability to deploy the same resources to a cloud environment. So these are the main requirements, even if we are using these tools to get started. So we can have Docker locally. We can use K3 as a lightweight Kubernetes distribution. We can use K3D, the K3s cluster on local or remote Docker containers. And GEPP is a tool to combine them together without any additional effort, without any parameter. It will automatically recognize your code, currently supports Python and WSGI apps. You only need Docker installed in your computer to get started. It will create Docker file, it will create Kubernetes YAML files, it will create a Kubernetes K3s cluster in your computer using K3D. It will forward the ports and give you an endpoint to connect to direct to the cluster. So let's see a demo of GEPP, and afterwards we will be done. Here is my cluster or my computer, and I am just running the command that I take from GEPP's repo. I'll press enter and it will automatically checking for Docker file. Okay, let's see what's going on here. Okay, I have already created a cluster. Let's delete cluster using K3D. I will also remove that Docker file to see how it generates automatically and rerun that command. It will not touch the existing files if it sees like Docker file. If there is a Docker file, it will just build that file. If there is no Docker file, it will create a Docker file for you and build image and take the image with the current commit ID. So if you just commit again, it will rebuild your image when you run GEPP, and it will import the image to the cluster nodes, so you don't require any Docker registry or container registry to push your image in order to provide your cluster to a chance of pulling the image. And it will automatically create Kubernetes deployment YAML file, service YAML file, ingress YAML file, and horizontal pod autoscaler YAML files for you. And K3D is used to create a local cluster. It is giving us an endpoint to connect. So ingress YAML file is deployed as well as other YAML files to the cluster. And here is our kubeconfig file. I will just give it the read access and export kubeconfig to that file. Let's cut it short. So if I run kubectl get pods, I will see my deployment is running here, and here is the address GEPP gave to me. I will add /number and wait for 2 seconds, and it's giving me the answers. So without any additional effort, in an empty repo, even without a Docker file, it is automatically creates a Docker file, a Docker ignore if it will not able to find. It's tagging the image with the name of the directory we are running. It's configurable, by the way. And the last commit ID is added as a tag. And afterwards, it's generating Kubernetes YAML files and deploys, create a local Kubernetes cluster, deploys that YAML files to that cluster, and afterwards we are ready. So let's go back to the slides. If you are curious about how it's working, here is a summary. And finally, it's creating a JSON file for deploying a cluster with Terraform to Azure Kubernetes service. More provider support is planning, and we are open for contributions. And here are some resources, and thank you for joining my talk. And if you want to connect with me, here are the details. Goodbye.